Hi everyone, I'm Xiaopei Wu from Zhejiang University. Here I will introduce Sparse System towards high-quality 3D selection with depth completion. The code link is provided at the bottom right. Currently, LiDAR-only 3D detection methods inevitably suffer from the sparsity of point cloud. Many multimodal methods are proposed to alleviate this issue. However, the different representations of point clouds and images make it a big challenge to fuse them. Previous works use a cross-AI fusion strategy that directly concatenates 2D LiDAR AI features and 2D image AI features. But 2D image AI features are usually mixed with features from other objects or backgrounds, which will confuse the model. Additionally, due to 2D image data cannot be operated like 3D LiDAR data, many data augmentation approaches are difficult to deploy in multimodal methods. For example, we can easily rotate point clouds of each object for data augmentation, but it's difficult to rotate image patches. To this end, we propose to convert 2D images to 3D pseudo-point clouds with the help of depth completion. In this way, the representations of point clouds and images are unified, which is very convenient for multimodal fusion and multimodal data augmentation. Now, let's see the pipeline of OSFD. We can divide the pipeline into 5 steps. In step 1, we generate a pseudo-point cloud with LiDAR point clouds and images. In step 2, the LiDAR point clouds are used to generate proposals. In step 3, we use the proposals to clone pseudo-point clouds. In step 4, we extract raw AI features and pseudo AI features. The pseudo features are extracted by ORCP convolution. In step 5, the raw AI features and pseudo AI features are fused with OR3D guide, and the fused AI features will be used to predict the final bounding boxes. By the way, we let the raw AI features and the pseudo AI features predict bounding boxes separately to regularize our network. In terms of architecture, OSFD can also be divided into 3 parts: their LiDAR string, pseudo string, and substance fusion head. Next, I will introduce each module of our method. With 2D images converted to 3D pseudo-point clouds, we can use a 3D AI to crop 3D LiDAR point cloud and a 3D pseudo-point cloud, which means that the AI features from LiDAR point clouds and images can be fused in a more fine-grained manner. Due to the same representation, we can perform data augmentation on pseudo-point clouds, same as the LiDAR point clouds. To solve the occlusion issue caused by some complicated data augmentation, we propose to project pseudo-points to their original image space for neighbor search. To extract features of pseudo-clouds efficiently and effectively, we present a CP convolution, which searches neighbors of pseudo-points on the image domain in an AI-aware manner. Here is a comparison between our method and other state-of-the-art under-kitted test set. Our SFD ranks first on the kitted 3D car detection leaderboard. Here are 3 situations where our SFD outperforms our baseline Roxo RCNN. Our SFD can provide more accurate predictions on objects with sparse LiDAR points thanks to the dense pseudo-point cloud. Thanks for your watching.